You ever wonder how these massive industrial chemical plants operate without just, descending into absolute chaos? I mean, picture a modern chemical plant as this massive, incredibly high stakes kitchen. We're talking miles of complex piping, towering distillation columns, and these giant roaring reactors. But instead of spatulas and measuring cups, the ultimate tools of control here are abstract math and fundamental chemistry. So, welcome to this explainer. Today we're going to unlock the operator's toolkit. We'll explore the invisible calculations and the chemical laws that keep these colossal facilities running safely and, of course, efficiently. Okay, let's dive right in. Here is our agenda for today. We're going to start with the language of precision, then move into decoding chemical reactions. After that, we'll explore the rules of equilibrium, look at matter, pressure, and flow, and finally wrap the whole thing up with statistical process control. All right, kicking things off with Section 1, the language of precision. In an industrial setting, precision is quite literally the thin line between incredible success and utter disaster. Before an operator can even think about controlling a chaotic process, they absolutely have to measure it using a universal language. And the foundation of that language? It's the base SI units. You've got your kilograms for mass, meters for length, Kelvin for absolute temperature, and the mole for the amount of substance. This standardization is totally crucial. When an operator sitting in a control room reads a gauge, those numbers have to mean the exact same thing to the engineer out on the floor. It guarantees perfect communication across the entire plant. But here's the thing, measurement isn't just about the units you use, it's really about certainty. In science, and especially in heavy industry, all numbers are based upon physical measurements, and inherently, every single measurement has some degree of uncertainty built in. I mean, a standard ruler just can't measure something to 10 decimal places. And that brings us to significant figures. These are the specific digits in a number that carry real, meaningful information about the actual precision of that measurement. Now, what's really interesting about this slide is the difference between 14 and 14.0. In a high school math class, sure, they have the exact same value, but in a chemical plant, they are communicating vastly different things. Writing 14 is basically just a rough estimate. It means the true value could be anywhere from 13.5 up to 14.4. But 14.0? That trailing zero is incredibly significant. It is a measured guarantee that the value is precisely 14 point something. It makes it 10 times more precise. In a high-pressure reactor, that specific level of precision could literally be the difference between a smooth operation and a complete catastrophic plant shutdown. Moving right along to Section 2, decoding chemical reactions. Once an operator can precisely measure their environment, they basically become a chemical conductor, orchestrating all these different types of reactions. Here are the four main types they oversee on a daily basis. First, you have combustion, like the rapid reaction with oxygen inside the plant's massive boilers to create steam. Then there's replacement, where ions are actively swapped out. This one is heavily used in water treatment to get rid of hard minerals. Next up is neutralization, which is the super delicate act of balancing pH by removing excess acidic or alkaline ions. And finally, redox reactions, where electrons are transferred between substances. That's the underlying chemistry behind things like rust forming on pipes. But an operator can't just throw a bunch of chemicals together in a vat and hope for the best, right? They use a technique called material balancing. Think of it as the ultimate form of recipe scaling. Step 1, you ensure the chemical equation is perfectly balanced, meaning atoms aren't just magically appearing or disappearing out of nowhere. Step 2, use the periodic table to find the relative atomic weights. And step 3, calculate the actual physical kilograms of reactants that you need. This math is absolutely vital. It guarantees that expensive raw materials aren't wasted, and much more importantly, that absolutely no dangerous, unreacted chemicals are left floating around in the system. Which brings us to Section 3, the rules of equilibrium. This is where we get into the real philosophy of chemical control. We're dealing with reactions that don't just move in one simple direction. See, many reactions are reversible, naturally reaching a state of equilibrium where the forward and reverse reactions are happening at the exact same rate. But operators don't want a stalemate, they want products. Enter Le Chatelier's principle. It states that if you stress a system by changing pressure, temperature, or concentration, the reaction will literally shift to lessen that stress. So operators essentially use this rule to trick stubborn reactions. By constantly removing the product or strategically altering the pressure, they force the reaction to keep moving forward, yielding way more product. And temperature is a massive stressor that we can manipulate. We generally divide reactions into two thermal camps.
You have exothermic reactions, which release heat and physically warm up the container. Then you have endothermic reactions, which take in energy and actively cool the container down. So, if an operator wants to push an exothermic reaction forward, they might actually cool the reactor down. The reaction thinks it needs to replace that lost heat, so it works harder and creates more product. It's this brilliant, invisible game of chemical tug-of-war.
Let's zoom out a bit for Section 4, matter, pressure, and flow. Getting to the macro level, how do operators manage the actual physical state of materials flowing through miles and miles of plant piping? Well, it all comes down to molecular structure. Solids have molecules packed tightly together in a crystallattice. They just vibrate in place. Liquids have much weaker cohesive forces, allowing those molecules to slip over one another and flow smoothly through pipes. But gases? Gases have vast amounts of empty space and practically zero cohesive forces. They completely take the shape of their container and are highly compressible. Understanding these fundamental structural differences is what dictates an operator's entire strategy for control.
And because gases have all that empty space, manipulating them is seriously high-stakes work. When an operator increases the pressure on a gas, they are violently forcing those molecules into a tighter and tighter confined space. This drastically increases the number of collisions between the atoms. And more collisions mean a massive, rapid spike in the chemical reaction rate. It's an incredibly powerful tool, for sure, but one that requires intense mathematical precision so that the pressure doesn't just completely overwhelm the vessel.
Finally, we hit Section 5, Statistical Process Control. To keep this entire chaotic system running safely, we rely on a statistical watchtower. And to understand exactly why we need statistics, just look at this number, 6.022 times 10 to the 23rd power. That is Avogadro's number. It represents just a single mole of a substance. Think about that for a second. An operator isn't managing a dozen moving parts on an assembly line. They are managing billions of trillions of molecules simultaneously, all reacting, heating up, and colliding at once. You can't possibly track that individually. You absolutely must use statistical math to keep track of the process as a whole. And that's exactly where statistical process control, or SPC, comes into play. It is essentially a mathematical cage built around the process. It's a graphic technique used to monitor standard deviations and variables over time. By tracking these data points against calculated limits, operators can identify abnormal, dangerous outliers long before they snowball into catastrophic plant failures. It all starts with a really simple data log, kind of like this one. Throughout the day, operators take multiple readings of a variable, let's say temperature. They calculate the mean, which is just the average of the readings, and the range, which is the difference between the highest and lowest readings. But let's be real, staring at a table of numbers isn't exactly efficient when alarms start ringing. They need to visualize it. So this data ultimately builds into a control chart. And this brilliantly illustrates the genius of SPC. You have your center line, right there the process mean. Above it is the upper control limit, and below it the lower control limit. Now, these aren't just random guesses, they are highly calculated statistical boundaries. If the data points bounce around randomly between those limits, the process is safely contained. It's just normal deviation. But the absolute second a data point breaks past that upper or lower limit, the operator instantly knows the process is spiraling out of control, and they have to jump in and intervene immediately. From significant figures to Le Chatelier's principle, right through to statistical control charts, a modern chemical plant is just a masterpiece of applied science. So I'm going to leave you with this final thought. The next time you pick up a manufactured product, whether it's a plastic water bottle, a refined fuel, or a purified medication, ask yourself, what invisible, high-stakes mastery of math and chemistry was required to keep it perfectly in control? Thank you so much for joining me for this explainer, and keep questioning the world around you.